Okay, and now you can start.
Okay, thank you again for the introduction and thank you for having me here. It's a pleasure to be here virtually with you. So the topic of today's seminar is machine learning and more specifically what machine learning can do for gravitational wave astronomy. So I shouldn't spend too much time explaining to you what multi-messenger astronomy is, since this is the topic of this whole series of lectures, but I would just want to briefly explain what is my way of seeing multi-messenger gravitational wave astronomy. So you start with a detector, the LIGO, Virgo detector, GEO, CAGRA, that will make a detection, which means that they see in their data some gravitational wave candidate signal. Then after this, the second step is to just do some parameter estimation, try to understand what are the properties of this signal, and most important of all, what kind of object collided, if it's a binary black hole or a binary neutron star, and where in the sky. Once we know where the object is on the sky, we should alert our electromagnetic counterpart searches. And for example, here there were Fermi and integral, especially in Fermi, were already detecting the gamma ray burst from that. But then, you want the optical and radio telescopes to look out and find the electromagnetic counterpart. And this is what happened for this, the binary neutron star signal that you all know. And then after that, of course, it comes a lot of more sophisticated observation and taking spectra and following up what happens. So you can imagine that in all those steps, machine learning could help. And so I tried here to give you my view of where machine learning can improve all of this. So there's a lot going on the detector side, as you can imagine, because you can just have more candidates, more signals if you increase the time the detector is up, if you can improve the quality of your data in terms of noise and spurious background. But then also you can imagine that machine learning might be useful in those computational heavy tasks of actually digging through the data and finding the candidates. And then after that, also parameter estimation based on Bayesian inference is really a heavy, computationally heavy process. And when you have to go through a lot of data. So those are the places where machine learning turned out historically to be very, very useful. And then of course, also in the rest of the chain, when you search for the electromagnetic counterpart, which galaxy you prioritize and how you optimize the follow-up, that's another place where machine learning can also be useful. As Rick pointed out, my background is more from the instrumental point of view. So my talk will be a little bit skewed toward the first part. So the parts that are closer to the detector. So how you can actually improve the detector, how you can improve the quality of the data of the detector. And I'll go as far as discussing a little bit how parameter estimation can be improved using machine learning, or could be improved using machine learning. So let's try to understand what this is all about. So this graph here shows you, if you want, the evolution of the number of detections we had as the LIGO Virgo network during the 3 observation run, or the 2.5, I should say, because this shows only what happens up to the first half of the last observation run. And you see that instead of having days here on the horizontal axis, we have basically the effective volume that we could observe, which is the product of the volume multiplied by the time of observation. Because it's clear that the larger volume you observe in the universe, the more events you can see, and the longer you observe and the more events you see. So if you want to oversimplify, the amount of science you can get out of your detectors depends on the number of events and the quality of the event. And so that depends on the observation time, so the duty cycle, on how far you can observe, so the sensitivity of your detector. And so it's clear that if you improve the detector in terms of robustness, time up, or in terms of how far you can observe, then this, of course, has a direct payoff. But also you can imagine that you can improve the sensitivity of your searches, in the sense that you can reduce the amount of background glitches, so reduce the amount of spurious signal that you have to dig through, and improve the efficiency and maybe the coverage of your search. And of course, then once you get some events, how much astrophysics you can get out of them depends, well, again, on how many events you get, but also on the precision of how you estimate the parameters of the system that created the signal. And to do that, you also need to have precise estimation of the waveforms for the gravitational wave signal. And ideally, you would like to do all of this very fast. So as soon as you get a candidate, you can send out an alert to all the astronomers of the world to just point their telescopes or whatever instruments they have and try to look up. So this gives you an idea of the motivation of all the places where it's important to improve the detector. And then I want to try and explain how machine learning can be useful in most of those places. So let's start with the first part. So how machine learning could improve the detectors. So you already had a seminar early this week on how the gravitational wave detectors work. So I'm not going to spend too much on that. The point is that, as you can imagine, as you know, they are very complex systems. So basically, if you oversimplify, they're microscopic interferometers, but to reach the high sensitivity we need, they use a lot of optical tricks, if you want, to increase the sensitivity, increase the circulating laser power. And our test masses have to be isolated from ground motion. And there's a lot of technologies that increase a lot the complexity of the system. And one way to pay for this complexity is the fact that ideally your detector is, the sensitivity of your detector is limited by some fundamental disturbances, if you want, some fundamental noise sources. So one would expect quantum noise, basically the counting noise on the photons that hit your detector, so that are circulating into your system, or thermal noise from the Brownian motion of the atoms making your mirror and test masses. But of course, in the real system, there are a lot more contribution of what we call technical noises, which just means that you don't have to break any laws of physics to improve them. It's just that the design of the detector is somehow limited, or you have some disturbance or some spurious noises coming in from places you weren't expecting. So you have somehow to improve them. So this graph I'm showing here is an example from the Hanford detector during 03, so the last run, and shows, first of all, the improvement of the sensitivity from yellow to gray to blue over time, when people like me and the other scientists in the LIGO collaboration work hard to improve the sensitivity. But then you also see that if we sum up all the stuff that we know, all the noises that we can identify and know, we get to this black curve here, which is different from the blue curve, meaning that there's still something to understand, there's still something to improve there. So this is an important place where the discovery algorithm for machine learning could also be important. So, and maybe I should mention that you see a few of these plots. For those of you who are not familiar with power spectral density, so this shows you how sensitive the detector is for each particular frequency. So you can imagine that if you had a single monochromatic gravitational wave 100 Hertz, then if the amplitude is below this level that determines the sensitivity of your detector, it means that the signal to noise ratio is below 1. So this is really difficult, almost impossible to see that. If instead, if you have something which is larger than that, then it's easier. And the larger it is, the easier it is to detect. So you would like to have this curve as low as possible. Of course, most of the signals we've seen so far, they're not monochromatic. They just like sweeping through. So you have to be careful when you compare a signal which is sweeping in time with these curves, but it still gives you a good idea of what's going on. And it's a nice way to summarize how much you know about your detector. So in the ideal world, well, in the ideal world, there are no noises. And so your detector is limited by the fundamental quantum noise and thermal noise. Of course, this is never the case because you always have some spurious noise contributions that will show up. You did not expect them. And so you have somehow to improve that. If the noise is witnessed by another auxiliary channel, so not the main signal that records gravitational wave, but some of the many other monitoring channels that we have around the interferometer, if the additional noise is witnessed somewhere and it couples into our gravitational wave signal, in a linear and stationary way, then we dealt with that many times in the past. So we know that we can do either some online or some offline subtraction, because it's a linear system. It's easy to estimate the transfer function or the coefficients for the coupling. And then you can just do subtraction that can happen directly online in real time on the detector, or maybe you discover that issue later, and then you can do some Wiener filter or transfer function analysis to subtract the linear coupling noise later on the data. And this is something that it's well known. It's been done in the gravitational wave community and in all the other signal processing communities for a long time. The problem comes when you start having some noises that are coupling in a nonlinear way. Saying nonlinear is literally only saying that the coupling is not a linear function, so it can be anything. So of course, there's no way you can model the most general possible non-linear coupling, which is shown here. You can imagine that the sensitivity of the detector is some irreducible background noise plus a function of a bunch of auxiliary channels. The only thing you can say is that this function must obey causality. So you can depend on those signals only for times in the past, but that's still a lot of possible functional forms. However, in most of the cases we are dealing with, we expect that the deviation from linearity is pretty small. And the reason for this is that we work very hard to set up control systems such that our detector is as close as possible to the linear working point. Of course, there are always fluctuations, but the fluctuations are kept as small as possible. Still, we see either quadratic coupling or non-stationary coupling. So you can imagine that this function is simply a quadratic form, or when we say non-stationary, it means that you can imagine that it's instant by instant, this function is linear, but the coefficient of this linear coupling changes slowly over time. And so it's still a non-linear coupling if you look at it globally, but time by time it's sort of linear. And you see two examples here. For example, you see that in this spectrogram, so this shows as a function of time how much power you have at different frequency in one of the advanced LIGO detector. And normally everything is clean and stationary. So you see that there is no fluctuation over time. But instead you see that if we were, in this case, we were on purpose increasing the noise in the detector by perturbing some auxiliary channel. And you can see that the coupling is no more stationary. There are areas and times when the noise is lower and times when the noise is higher. So this is an example of non-stationary coupling. Or you can look at this plot here on the other side, and you see the 60 Hertz line, which is the electromagnetic line coming from the main power lines. So remember that in the United States, the main frequency is 60 Hertz, not 50 like almost everywhere else in the world. And you would expect that this perturbation, which is everywhere, would couple only exactly the 60 Hertz frequency, but you see those mountains on the side that are symmetric, is what we call sidebands. It is an indication that the coupling of the 60 Hertz is not stationary, but it's fluctuating at those frequencies over time. So if you try to apply some linear subtraction in this case, of course, you don't get any improvement except at the actual line. So that's why we developed some algorithm to deal with non-stationary and quadratic noise couplings. I don't want to go into the details, but the key here is that this is the first algorithm that is, if you want, inspired both by machine learning and by our understanding of the detector. So it's what I call physics-informed machine learning model. So it's not the most general machine learning model, a neural network or whatever you like. It's just a simple coupling model like the one shown in this equation, but then you can use algorithms from machine learning to actually learn what are the parameters of the coupling. And you can see that the effect, this is maybe not the most general nonlinear model, but it's an example of a good enough algorithm that can improve the sensitivity of our detectors. And so, for example, this left plot shows you that while we were injecting that auxiliary noise that was showing the spectrogram, you start from this blue curve here. So the sensitivity is really a factor of 1,000 worse than what it should be. You can do only a linear and stationary subtraction, and you would get to the green curve here. Then if you apply a full non-stationary subtraction, you can get down to the red curve. So you see there is a lot of improvement there. And similarly, this kind of algorithm is able to outperform the linear subtraction in the case of modulated couplings like the 60 Hertz. So we start from the blue, which is the same that I was showing earlier. Then if you only remove the stationary contribution, you only get rid of the main line. So you see the line going down to the yellow curve here. But then if you allow this coupling to be modulated with this machine learning inspired algorithm, you can actually get down to the background, which is this red curve here. And the key point of this is that this kind of algorithm also gives you results that you can interpret. So you can look at what is the source of the modulation. It is an important information for us because, at the end of the day, what you would like to do is to really go back to the detector, understand why this coupling is modulated, and do some engineering or control fix to get rid of this. So you might ask, why not using a neural network for this? Because we all know that neural networks, especially deep neural networks, are, at least from a mathematical point of view, universal approximators. If you get a big enough neural network, you can approximate, in principle, any nonlinear complex function. So the point here is that this has been tried, of course, and you can see two examples down here. So for example, a neural network has been used to learn how to subtract the linear and stationary noise that I was mentioning a couple of slides earlier. And you can see that you start from the blue curve, and the green and the orange are two different ways to subtract this noise. The orange is the Wiener filter, a classical linear noise subtraction approach. And you can see that the neural network was able to learn this linear subtraction. Of course, you're using a neural network to subtract noise, you're using a neural network to subtract noise that is coupling linearly. So it's kind of overkill because you already know that you can do that in other ways. You can also try to reproduce the results of subtraction of the auxiliary noise that I was showing just in the previous slide. And you can see that the neural network gets to the level shown here in orange, which is not as good as the level that you can get with the simplified physics-informed algorithm before. And the reason here is that neural networks have difficulties in handling data with long history. So in this case, you have some noise which is fastly changing around 100 Hertz if you want, but the modulation is changing over a time scale of a second, 10 seconds. So this neural network should be able to handle long time series. And either if you use convolutional neural network or recurrent neural network, it's always very hard to train them to the optimal level when they're dealing with very long series. This is a well-known problem of neural network. And there's a lot of research on the machine learning community to improve the memory of the neural network. So this is why we didn't want to use a neural network, because it's always harder to train, even though ideally it should be able to get to the same performance level. So once you've done what you can to reduce the noise in your detector, you're not done, because you still have to work to improve the data quality of your detector. So this means that there are what we call glitches, and glitches are very short transient noises, like you can imagine literally like small blips or small increase in the power on particular frequencies, or not that slow. And the problem is that when you look for gravitational wave signals, every time you have a loud enough glitch like that, it will trigger a spurious response in your searches. And you can see here in this graph that the trigger rate due to these spurious glitches in the two LIGO detectors, for example, is pretty high. So even if you restrict yourself to SNR above 8, you have one every, I don't know, 100 seconds or so. Of course, the number of coincidence glitches that happen at the same time in both detectors is much lower, but still, even statistically, you can have random coincidences that are not great. So what you have to do is to figure out ways to identify those glitches and be sure that they are not gravitational wave signals. And the way to do that in most cases is just look at other signals in the detector and develop what we call a veto. So saying every time you see a possible trigger candidate in the main gravitational wave channel, you have to look at other channels and see if you see something similar somewhere else. So if a glitch happening in a magnetometer somewhere in the interferometer, in coincidence with what is happening in the gravitational wave signal, you can be reasonably sure that that's not a gravitational wave because your magnetometer is not sensitive to the gravitational waves. Doing this kind of veto has a very significant impact. If you look at this graph here on the right, you see the cumulative rate of triggers as a function of the signal to noise ratio, so the amplitude if you want. If we didn't do any data quality, any veto at all, we would get this distribution, which is the red curve. So you see that you have tails going up to pretty high SNR. After the kind of data quality vetoes that we do right now, you can reduce a lot. So this is a logarithm scale. So this is really a huge reduction. And this is really important, especially because you see that the background, the measured background is basically non-existing above SNR of 12.5 and so. And this dashed line here shows where one of our low SNR events, some of those that we detected on the first science run, where it was sitting. So if we were not doing any data quality, this event would have been completely, in the sea of the background. Instead, after this improvement, after this data quality cuts and vetoes, it is well above the background. So this is an important work to do. The way it's done so far, it's mostly human-based activity. So you just try and look at the most allowed glitches and sift through and go through all the different auxiliary signal, and then somebody discovers a correlation that's checked, and then that is then promoted to a full-fledged veto. You can see here the opportunity of using machine learning because it's you have a lot of data, you have a lot of glitches, you have a lot of information because you can even produce full waveform or spectrogram, like in this case, or the glitches. And it's a typical example of a classification or correlation that you can, or regression, even if you want, where machine learning is working pretty well. One of the problems here is that a lot of the good algorithms in machine learning that can handle these kind of things are supervised learning. So you need to have a lot of examples with labels. So you have to need something like this thing here and say, hey, this is a gravitational wave signal. And then look at this. This is not a gravitational wave signal. This is a glitch of the class A. This is a glitch of class B, and so far. And so some activity in this was started with the Gravity Spy project, which is in between machine learning and citizen science. So the idea is that you have a lot of online, citizen, not physicists, not scientists, not necessarily scientists, that can look through all these images here and give a classification based on pre-existing classes. And then you can use those labels to train a gravitational wave train a machine learning algorithm. And this is what the Gravity Spy project does. And you can see the confusion matrix here. So it's basically telling you what is either the row or the column is the real class and the other is the predicted class. And you can see that in most cases, you get something along the diagonal with a lot of ones there, which means that your system is really able to the algorithm is really able to identify those glitches just by its morphology. Of course, it's always a little bit tricky and dangerous to only look at the morphology of the signal in the gravitational wave channel, because you might be killing something which is a real gravitational wave signal. It's always better if you're able to do a veto based on other channels that are not sensitive to gravitational waves. And this is what is done by the IDQ veto, which is again, based on machine learning, and it's an example of what happens after training is shown here. So this is a gravitational wave signal, but you see the low frequency component here there was an excess of power in the low frequency, which turned out to be in coincidence with a glitch on one of the auxiliary channels. It doesn't really matter what this is, but it's an angular motion of some of the mirrors if you want. And then you can see that the system was able, after being trained and working in real time, to actually identify that these could be vetoed by looking at those other channels. And so this is the first example of how machine learning was applied to first train some classifier, some veto generator on training data, and then deploy it on the real system and actually improve the science. So, as I said, it's this kind of veto generation of data quality is really important. It's a place where machine learning could really contribute a lot, because it's a clear example of big data. We have thousands or tens of thousands of channels that are recorded and written to disk. So you can imagine a machine learning algorithm could be able to go through all this data and trying to find correlation between what we see as spurious events in the main gravitational wave signal and what's happening in the other signals. And I say what's happening and not necessarily glitches, because you can imagine at least two ways you can produce a veto from an auxiliary channel. What is being done so far is a one-to-one correspondence, if you want. You see a glitch in the gravitational wave signal, you see a glitch in another signal, you say, okay, there are two glitches, one cannot be a gravitational wave, so this is vetoed. But then you can imagine also some more complex way and some feature in an auxiliary channel could correspond to a glitch. For example, you might have an actuator with saturates, so some signal that goes flat, or some signal crossing some level where there is some faulty electronics. Every time you cross a level, you have something going on. Or even when some signal is changing too fast, something cannot keep up, and so this creates spurious disturbances. So this is a more complex kind of correlation, but again, you can imagine that if we had efficient and robust data mining algorithms and some sort of classification correlation algorithms, these could be very, very useful. And I just have a few references down there of works where this is being studied, as being considered.
Gabriele?
Yes.
There is a question from Ilsang. I will let Ilsang tell his question himself if he wants to. Maybe I just a call that we've been talking, you've been talking for 30 minutes, or there might be other questions for this first part of the talk.
Of course.
And please go ahead. Do you want to need to read your question?
Okay, so basically just the question about the number of components in the machine learning based this noise reduction. How do you decide, okay, how many components do you need in the end to get an optimal result?
Well, like in most cases in the machine learning applications, it's a little bit of a trial and error. So it depends a lot of what kind of algorithm you are developing in machine learning. So a little bit of understanding of your system is of course important. So that's why I was stressing earlier the idea of physics informed machine learning algorithm. So from that, you have some understanding of what is the mechanism that couple the noise. So you try to put enough complexity in your machine learning to capture that, and not less than that, no more than that. But then of course it's a matter of trial and error. So at some point you have to try different hyperparameters if you want, and just find the one that works better.
Okay, so my question is really more or less towards, okay, how do you convince yourself at the end of the process, okay, I'm pretty much done. What I see now is a pretty much noise. Would that be a better question?
Well, so of course you will see, for example, if you are subtracting noise, will see that the sensitivity of the detector increases, and you can never be sure that you've done all you could be doing, but of course, you can, for example, in the case of the subtraction, the 60 Hertz harmonic, you saw that the line was almost completely gone and all the structure around it was gone, and you're reduced to some sort of background level. So that's what convinces you that that is optimal for that application. But of course, there's always room for improvement, and at the end of the day, it's you're never sure that you subtracted or you got rid of all the noises that you could, but you just it's an example where the good enough is enough. So you get an improvement, you deploy it, and then you move on, and it's an iterative process.
All right, thank you.
Of course, you're welcome.
I see another question for Can. Can, do you want to ask your question or do you want me to?
Yeah, okay.
Right.
First, I'm sorry if I missed something, but in the last slide, can you come back to the last slide?
You mean this one?
Yeah, this one. On the right side, that was a gravitational wave signal, right?
Yes.
Yes, but when after you apply IDQ veto, and I saw that there is a four parts of the signal that relate to the four, I don't know, maybe the four malfunction or something. So how to come up with the conclusion that this is a real signal?
Yeah, so the what's happening here, you see that the content of the frequency, so if you want, most of the power in the glitch as seen by the non-gravitational wave channel is all concentrated at lower frequencies, while you see that the gravitational wave channel has a lot of power concentrated at higher frequency. So this is a veto algorithm that focus on one-to-one correspondence, so time and frequency coincidence. So what happened here is that you identify that there is a glitch at that point, then you can actually get rid of that glitch by subtracting it, and what you are left is something that is still meaningful, and so you see that you still have a gravitational wave signal. Of course, this is the worst possible case when a glitch is superposed to a real signal. And the only reason this was recovered as a real signal is because there is this, if you want, separation of frequency. If the glitch extended all the way to 200 or 300 Hertz, as you see there, then we had no way at this point to say that this was a real signal. One more reason that it's important not only to develop vetoes, but to understand the origin of the glitches and get rid of them.
Okay, thank you.
You're welcome.
Very good. Are there any other questions for Gabriele? I don't see any in the chat, nor I see hands up, so I believe we can continue.
Okay. So that was a good point to stop for questions because I'm moving to a different topic here. So another way you can improve, of course, the amount of data and the result you have is by improving the robustness of your systems, which means improving the duty cycle. So by duty cycle, we mean what percentage of the time the detector is up and running. And if you look at a distribution of what, for example, happened at the Livingstone LIGO detector over one of the previous runs, you see that we lose something like 15, 16% of the time due to what we call lock-in and environmental. So environmental is mostly means that there was a big earthquake somewhere in the world and knocked our detector off the high sensitivity state. And locking is basically the time it takes to go from a completely uncontrolled system to the final high sensitivity state. So you can see that if you improve on that, it would be very important because you can increase the amount of time your detector is up. So to improve that, you can either try to predict and prevent these events. So of course, we are not predicting earthquakes in the sense that knowing where they happen, but since the earthquake the seismic wave takes some time to travel from wherever they happen to the detectors, we can have some look at the geophysics data and try to predict the arrival time and the amplitude of the signal when it arrives to our detector. And there's some work on that. And then if you know that there's an earthquake coming in, you can try to tweak the control system of your detectors to just make it more robust for that time. Maybe at the price of sensitivity, but still you avoid being knocked off the control area. And then, of course, the other things you can do is to just try to be fast at recovering. So improve what we call the lock acquisition sequence. I will try to briefly go through that because that's a topic that I'm especially interested in developing. So our detectors are pretty complicated. And so we have to, since you have to maintain the control to within a linear range, we can be, the order of 10 to the minus 15 meters or something like that. You cannot do that by just looking at every single mirror locally, but you have to measure the distance between the mirrors and the pointing of the mirrors in some sort of global way. And the only way to do that is by using optical signals that are very sensitive, but the problem is that a linear response exists only for a very small fraction of the phase space. So if you would just wait for your detector to wander through the linear area and then switch on some classical linear controller there, this would be possible in a fraction of the phase space, which is lower than 10 to the minus 9 or something like that. And so you need really to have some sort of non-linear smart way to go from the uncontrolled state to the control state. So this is an example of where machine learning could be used to develop a control system. And if you mean the classical, or well, classical, it's a wrong term because the most recent development or the way machine learning enters in control system is through what is called reinforcement learning, which is an idea of having some sort of a agent that will look at your system and try to develop what is called a policy, so a control model to try to fulfill some task. In our case, the task would be to bring all the degrees of freedom of our system in the linear range and keep them there, or at least bring them to the linear range, because once they're there, we know how to maintain those points. And reinforcement learning is set up exactly like this. So you have some real system, you have this algorithm that will try to maximize some reward, which is the case is, for example, how quickly you can get to the control state. So this seems fantastic. So it's because it could be completely model agnostic. You don't need to know how your system works. And even if you know a little bit, you can use this algorithm to improve the model. So this seems exactly what we need. The problems is that it's very time consuming. You can Google inverted pendulum and reinforcement learning, and you see that it takes thousands of iterations for a machine learning algorithm like this to learn how to balance a stick like you would do with no problem on your hand. And so it needs many, many attempts, thousands, if not millions of attempts on the real system. And this is expensive. We cannot afford to leave a machine learning algorithm to play with our detectors for days, weeks, or months. And it's also risky because initially the system has no idea what it's doing. So you can have random policies that could perform actions that are actually unwanted or even risky on a delicate system, which is our detectors. So that's why there hasn't been a lot of reinforcement learning studies for our detectors, but we are ramping up on that. Another approach would be to just try to use a neural network to construct a nonlinear state estimator. So we have, as I said earlier, we had a lot of optical signals that are related to the state of the system, but in a nonlinear complex way. And so you could imagine to have some neural network or some other machine learning algorithm that will take all this signal and try to predict the actual state. The problem here is that we don't know what the actual state is in the real system, because if we knew, we already had an algorithm to try and acquire the control of the system. So the idea is that you need to start in simulation. So you need to have a good model of your system and try to train a neural network on the simulated data. And so the idea is that you would go through a cycle like this. We start with a model of your system. You can simulate a state. Then you use your model to simulate the output, and then you train a machine learning algorithm to solve the inverse problem. So go from the simulated output to the actual state. Once you have something which works well on the simulated system, then you can deploy it in the real system. If your model is close enough to the actual system, then you actually have a good estimate of the unknown state. And that is what you could use as a starting point to develop a simple algorithm to acquire the control of the system. Because then instead of having a good estimate of the state, which is valid only on a very small fraction of your phase space, you have this nonlinear state estimator, which is able to give you a good guess of where the system is sitting everywhere in the phase space. And if you have that, it's very easy to just drive it to the 0 point if you want. And then you can imagine that once you have the system deployed, the machine learning algorithm deployed to the physical system, you can close the loop and refine the model based on the performance on the real data by extracting physical parameters or something like that, and go back again and do this cycle. So this is an interesting idea, and we are starting to work looking at that. And could be a promising way of making our control system more robust and scalable. And that closes the section about how we could use machine learning to improve the performance and duty cycle of our detector. Maybe I can stop a second, see if there are questions on this section before I move on.
Right, very good. Are there questions for Gabriele on this part? I don't see any.
Okay, great. So the last part here is how to see how machine learning could improve the actual analysis of the data. So you had the ideal perfect detector, the best you could build, and then you have your data, and you want to get some gravitational wave signals out of it. So the way the classical way to detect the gravitational waves is by doing matched filtering. So you see here a simulated example of noise going through our algorithm, and it's looking for a correlation with this pink curve. And you see that at some point, there was actually a peak there in the signal to noise ratio, and that's where a signal is detected. So this is the way most of our analysis is done, because matched filtering can be shown to be the optimal way to detect signals in stationary and Gaussian noise. So you can really see two problems here. Our noise is not Gaussian and it's not stationary. And also the other thing is that you really need to have one template like that for every possible combination of the parameters of the physical system. So you need to really have hundreds of thousands of templates covering all the possible space, for example, in this case, shown of masses of the signal. And this is how the analysis is done. You start with matched filtering for each single possible parameter, and then you end up with the final result, which is all the detections we had so far. So how can this be improved using machine learning? So the first ingredient you need are the waveform. You have to accurately cover all the possible parameter space. To get accurate waveform, and one example is shown in this slide, you really need to have a mixture of analytical model and numerical relativity simulation. And numerical relativity is especially important for the final part when you have the merger and the ring down of the event. And those are very computationally demanding. So it's not possible to have numerical relativity model run for every one of the 500,000 of templates you need. And so what has been done is to use some sort of phenomenological or surrogate or mixture of analytical and numerical relativity, but then that gives you still a too sparse sampling of the parameter space. So you need to use reduced order models or some sort of interpolation to cover the whole parameter space. And this is an example where machine learning is already being used and has been important. So there are just two examples of the most advanced, if you want, machine learning algorithms that can be used to extrapolate from a very sparse covering of the parameter space to the 500,000 or more of parameters that you need. And so people have been used different kind of interpolations. Here are some examples are showing you results of using Gaussian process regression or neural network, and they both show good accuracy. I think that the Gaussian process regression is showing a very good residuals in terms of mismatch, which is in the 10 to the minus 6 or so level, while neural networks are still around the 99% or something like that, but which is promising. And of course, the idea is that you will compute a few points and then have these interpolation algorithms that will be able to give you waveforms very quickly. So you don't need a full day or a week of computation to get the results. You can get it in order of milliseconds once your machine learning algorithm has been trained on the data. So once you have your whole templates, you can still imagine that running all that matched filtering through all these templates and all the data is very time consuming. And also the question is whether, matched filtering is optimal if you have stationary and Gaussian noise, which is not our case, unfortunately. So the question is there any other nonlinear detection algorithm that can improve on top of that? And this is very, very preliminary still, but people have been trying, started looking into using, for example, random forests to see if it was possible to improve the efficiency. And this is an example shown here on pretty old O1, so the first run of data, but you can see that there can be a significant improvement in the volume time product. So, in the basically the number of events you could get by using this random forest trigger generator instead of the classic match filtering. And you can see that you can get up to 20 to almost 40%, 30% improvement, which is significant because it means that instead of having an event every, 6 days, we have an event every 5 days. At the end of the run, it's quite a significant improvement. And you can also see something that I found quite interesting is that even the higher the masses of the systems are and the more you improve. And I believe this is due to the fact that the higher the masses and the lower the frequency of the gravitational wave signals. And we know that the non-stationarity and non-Gaussianity of the data is worse at low frequencies. So this is maybe a hint of what's going on here. And another interesting, more recent result is people use a deep convolution neural network to try and reproduce match filtering. I believe this is still with injections on real data, so it's not quite a real detection, but you can see from these curves that, for example, the bottom curve shows you the probability of recovering something as a function of the signal to noise ratio. So the light blue curves is what we get with the match filtering. So you see you need the SNR of the order of at least maybe 6 or 7 to be able to detect something with a significant false alarm probability. And using a convolution neural network seems to be working pretty much the same way at when the SNR is high, which is not a surprise. If the signal is strong enough, everything will see it. But then seems to be doing better at lower SNR. So when the signal is close to the noise, this convolution neural network seems to be more efficient at match filtering, which again, shouldn't be a surprise because we know that match filtering is optimal for ideal noise and our noise is far from being ideal. So this is a very promising result that we'll see how it can be actually deployed to the real systems.
Right, so I think Il-sung has just a question on this topic. Il-sung, do you want to speak up?
Okay, so do you have a plan for reprocessing old data using this new machine learning technique to see if you can, find the previously hidden the signal under the noise?
I am not aware of any plan going on, but I know that all the LIGO data up to the second observation run is now public, and there are groups that are working in reanalyzing those data using different algorithms, and they are finding more events on what we would call the marginal, so that are not very loud events, but kind of borderline between background noise and real signals. And since the algorithm is a little bit different, they are seeing more of those. And I expect that in a few months, we should release the entire first half of the third and last observation run of advanced LIGO. And so I expect more and more people will work and look into that. And some of them probably also using this new machine learning algorithm. And I'm very curious to see what's going to happen.
Okay, thank you.
Of course. So of course, I focus a lot on what we call CBC, compact binary coalescences, because those are the only events we detected so far. But those are not the only signals that we are looking for. So we are also looking for bursts of unmodeled signal or supernovae, signals from supernovae, and continuous waves. So application of machine learning in those two cases is not as developed as in the case of binary coalescence, mostly because, well, I guess mostly for historical reasons, but I just want to mention some references here if you're interested. So for example, in the case of a burst and supernovae, there has been use of convolutional neural network to search for modeled supernovae signals. So this is again a match filter-like problem. And then there's also use of machine learning for search-related data quality, so to reduce the effect of glitches or to reduce the background signals. And so this shows promising results, but they're not in a very developed state. And continuous waves, it's also, so we are looking for signals for pulsars, so that are almost monochromatic and they last for a long time. And you can imagine that since you have to look through a lot of data, those are very computationally intensive. So that's where deep learning and machine learning could be used to classify continuous wave sources, to look for known pulsars, or even for the most complicated searches for unknown sources. So I have some references here that you can look up later. So the final step, once you have a detection, of course, is to estimate the parameters of the system, so to understand what you saw there. And the way we do parameter estimation is based on Bayesian inference, and we typically use right now some sort of Markov chain Monte Carlo sampling algorithm to just go basically fit the parameters of your waveform to the actual signal you see in the gravitational waves, and then give you the probability, the posterior probability distribution of the parameters. If you have ever worked with the Bayesian inference, you would know that it's really very computationally demanding. One part of it is to generate all the possible waveforms. And so this falls back in what we discussed a few last slide ago, that having fast machine learning algorithms to generate accurate waveform is really important. But also, a parameter estimation run for one event can easily take days on a cluster of computers. So this is not scalable to the third generation detectors when we expect multiple events per day, very long signals and overlapping signals. So it's interesting to see if it's possible to use some other machine learning algorithm to completely get rid of the Markov chain Monte Carlo method and have, for example, a neural network or something like that that can predict the probability distributions. There has been some research using either deterministic or Bayesian neural networks or variational autoencoders or other sophisticated results. And an example of what's going on simulated data for now is shown here. So you see that the Markov chain Monte Carlo Bayesian inference will give you the green posterior distribution of some of your parameters. And the neural network is able to get that very, very close. So this is a promising result. Still in the simulated data realm for now. So I'm not aware of any work to actually make it deploy to the real systems, but this is promising because it will these neural networks can run in a matter of seconds instead of a matter of days. So that's really what would allow us to have a much better, much faster alerts for electromagnetic counterparts. And this brings me to my conclusions. which is, I try to, so it's really surprising how if you try to find online a map of the machine learning algorithm, everybody have their own map. And so I started from this one, and which is not exhaustive, not all of the algorithms are there, but I kind of circled in red all these kind of algorithms that have been somehow used or been tried in the gravitational wave community. So you can see that we are pretty much covering all the bases. So this is interesting, and a lot of them had already provided good results. I also added to my own, which is this physics-inspired machine learning algorithm, which is something that is not very much covered out there in the literature, because I guess, you know, it's not important to understand what is the next movie you want to recommend, or what is the customer, how to keep your customers. Maybe there's not much physics there, but who knows? And then also an area where there isn't a lot of work out there, but that is really important for us, is how to handle time series and long time series, which is something that is still limits for us. So that said, I want to finish with two kind of funny slides, if you want. So the first one is I Googled and I show you statistics of how many papers were published with the machine learning words in the title, and you can see a clear increase in the last decade or so, but sort of a steady rate of increase in the last few years. But then if you look at all the papers that have machine learning and gravitational waves, you can see that we are maybe following, we start a little bit later, but we are definitely increasing much faster than the trend for machine learning. So meaning that we are a little bit later on the game, but there's still a lot of increasing interest in machine learning, in gravitational wave astronomy, and for all the things that I explained earlier. And then I want to conclude with these slides, and which is just meaning that we have to be careful that machine learning is a powerful tool, but not necessarily always the right tool for the job. You don't want to overkill where you can solve the problem in some other ways. And with that, I thank you for your attention, and I'm happy to answer any more questions you might have.
Thank you very much, Gabriele. Very nice review. Thank you very much. Are there any questions for Gabriele? We had few questions during the talk, obviously, but on this last part. Yes. So Germano, do you want to speak up, or do you want me to read?
I can speak. Hi. Yes. The question is about the marginal events. In the case that you have detection of marginal events with machine learning, how can you be sure that you are redetected a signal and not an artifact of the machine learning? And it is just because I'm skeptical about machine learning in the sense that for me, I'm ignorant, it's a black box. So I have the output and okay, thanks.
So that's a very good question. And you can tell from this last slide that I put here that I'm kind of skeptical too, even though I am using machine learning for some of my work. But so I guess the important thing is that we need to use machine learning algorithms that are open to interpreting the results as much as possible, because it will be important to be able to look at the output of the network, and whatever machine learning algorithm, and when the machine learning algorithm tells you that there is a candidate, then it would be important to be able to understand why the machine learning algorithm made that decision. At the end of the day, it will all boils down to not just saying yes, there's a signal, no, there isn't a signal, but to provide a probability of the signals being real, so a false alarm probability if you want, and also an estimation on the parameters. So once you have that, which is the output of all our other algorithms. So you can say that any kind of data analysis algorithm is a sort of to some extent, a black box. But as long as you get an estimate of the false alarm probability that you can trust, and then a good reconstruction of the parameters, then you can probably be confident on the machine learning algorithm. The way to gain confidence is to run through simulated signals. So it's easy for us to have the real detector noise and to add artificial signals, just, you know, it's a matter of a digital plus really adding some signals. And then you can see if your machine learning algorithm is able to reconstruct, to recover those with what accuracy, with what efficiency, and then what kind of parameters you get out of that.
Thanks.
You're welcome.
Other question for Gabriele. Anybody wants to?
Can I ask one more question?
Sure, go ahead.
I know it's a bit weird, but since you already mentioned this, I'm going to ask this question. Let's say we have the signal with the very long period of inspiraling phase. Then obviously the LIGO operation 1, 2, 3 might not have enough time baseline to cover that. Then later, if you have a idea, okay, can you actually combine all these previous observation in a time series and then try to rerun this process to get more inference? Okay, if it's really, you know, the, you know, long, you know, the duration of inspiraling is there, then to do that, actually, how this machine learning can deal with the time gap?
That's a very good question. So, of course, you know, all our data is recorded and saved, so it would be possible to go back and look at what happened in the past. And it's actually part of the plans. Once you detect a possible candidate, for example, of a continuous wave, there are plans to go back and look if that's still there. I have no real answer for your question. I don't know how machine learning algorithms would deal with the missing gaps or missing data. I guess it depends a lot of what algorithm you're thinking to use. And also it's, I mean, I would even know how you would approach the problem of just feeding the, you know, years of data sampled maybe at a kilohertz rate to a machine learning algorithm to get anything out of it. I would imagine that you would have to do some initial preprocessing to extract some features to just do some sort of data dimensionality reduction of your data and then feed that to a machine learning algorithm. So probably the burden of dealing with missing data would be more on the preprocessing step rather than the machine learning step. But I'm just guessing because I wouldn't know what kind of algorithm you could use in that case.
Okay, thank you.
You're welcome.
Other question for Gabriele? I may have one. Can you go back to the big map of machine learning you were right? And you have this box of physics inspired learning, right? That I think connect with the algorithm you've been presenting at the beginning. And but I think you're characterizing this as a family of algorithm for machine learning. What would be the common feature? I mean, what would be the concept here? I'm not sure I'm getting here.
Yeah, of course, just, you know, putting it in a box that is separated from everything else is not quite right, because this is sort of more of a paradigm rather than an algorithm. So the idea here is that, so if you want to oversimplify, on one hand, you have the deep neural network approach, which is, I have no idea what's going on in my data. I have no idea what's going on into my machine learning algorithm. I just put there enough complexity such that the deep neural network can model everything. If I manage to train that network, I'm successful. I can classify my images, I can classify my glitches and so far. On the other hand, what I rather do is say, well, but it's not true that we don't know anything about our data or about our system. We know quite a lot actually about our detectors, for example. We have pretty good models of how the detector behave. So it would be important to leverage that knowledge and make sure that whatever machine learning algorithm we use will use that knowledge, which means, for example, doing model predictive controls, for example, or some research that's going on. For example, if you have a machine learning algorithm which is learning the evolutions of physical system, you can enforce conservation of energy, conservation of momentum, stuff like that. Or in this case, just saying we have a model of a system. If we know that, for example, if we have a bunch of measurement of our signals in the system at a time, we know how to restrict how they can evolve to the next time step. So this kind of information that comes from our physics knowledge of the system should be plugged in, and this has the advantage of constraining the machine learning algorithm. So we can be more confident that the machine learning algorithm is not going crazy and overfitting. And it also allows us to reduce the number of parameters we have in the machine learning algorithm, so speed up and improve the training. So I guess you're right, it's not quite a box there. It's more like a general idea, general approach for everything.
Right, I think it's what you're saying is that it's something intermediate between a fully parametric approach and a completely non-parametric approach. Something.
Yes, that's a good way to put it. Yes.
Okay. Any last question? Yes, there is a hand up by.
Yes. Yeah, so actually, maybe this is a bit of a follow-up on the previous question on a more concrete example, because I didn't quite understand how machine learning would help in the case of these continuous wave signals, which I think in terms of waveform are very simple, but very long. So could you perhaps clarify this?
Yeah, so first disclaimer, I'm not an expert on this, but I'll try to give you my view. So of course, it's not helping with the waveform, because we know that, so if we have a known pulsar, we have radio observation, and we know very well the frequency and the evolution of the frequency with time. So we know the waveform perfectly. But then you have to be able to go through the signal, through the data, and look for that waveform. So again, in stationary noise, a match filtering, a very long match filtering, which is basically a Fourier transform. In the case of, if there were no evolution of the frequency, you would do a Fourier transform. That's basically match filtering for a continuous wave, right? So that's ideal. But of course, our noise is non-stationary. So you can imagine that some deep learning or machine learning algorithm could improve on the match filtering. And then the other thing where it's probably important is that we would like to search for unknown continuous wave sources, which means that you have to search for all possible frequencies, all possible orientation in the sky. And the fact that the Earth is moving around the sun makes that the signals is actually Doppler shift of a significant amount. And even the rotation of the Earth is enough to Doppler shift the frequency a little bit. So you have to factor a different set of parameters for each position in the sky. So this is extremely computationally heavy. So far what people do is try to just go with an almost brute force approach. And you can imagine that machine learning, again, they seems to work pretty well every time you have a lot of data, a lot of parameters, you have to do a lot of searches that are machine learning algorithms could be more efficient to do this kind of, to help with reducing the computational burden of the searches.
Okay, thank you.
Welcome.
Thank you again, Gabriele. I think if there are no other questions, we are about to close the session. This is a final call. Right, so I thank you again. I think this closes nicely our first week of lecture. Next week, we are going to speak about astrophysics and gravitational waves, cosmology, gravitational wave cosmology, and data analysis. I think those are the three main topics that we are going to address in the lecture next week. So I hope you enjoyed the set of lecture we have this week, and we look forward for the next part. For those, and I mean, for for anyone, but especially for those who missed the Gather Town session this morning because of time zone issue or other reason, please let's gather now in this Gather Town and have a look to the nice poster that we have and have some informal chat. So don't forget to use your Chrome browser if you want the audio right. And with this, I wish you a good weekend to all, and see you on Monday morning for the next lectures. Thank you again, Gabriele, for the presentation today, and bye-bye.